Welcome to our module on logarithms. So first off, I want to ask you, what do you call a tree that can dance? A logarithm. Get it? Tina, this isn't even your subject. Bye. Sorry about that, girls. But anyways, what exactly is a logarithm? Well, everything in mathematics has an inverse. Alright? Subtraction is the inverse of addition. Division is the inverse of multiplication. So, logarithms are the inverse of exponents. By definition, we say that the logarithm of a number is the value to which the base must be raised to give that number. Now, what exactly does that mean? Well, to help illustrate and to help you understand, let's look at this example. If 2 to the third power is equal to 8, then we say that 2 is the base, 3 is the exponent or power, and 8 is our result. So, according to that, if we were to reverse it, we would write that the log of 8 in base 2 is equal to 3, which you can interpret to mean that 2 raised to what power gives you 8? The answer to that is 3. So that's exactly what this part over here means. So for this class, you are required to be able to write from exponential form to logarithmic form and vice versa. So our first example says, write 5 to the third power equals 125 in logarithmic form. So here our base is 5. So that is going to be the little number right next to the log symbol. So it's the log in base 5. And here you notice that 5 is raised to the third power, which is equal to 125. So our answer will be 3 because that's the power. But it's the log of what in base 5 that is equal to 3? It's the log of 125 in base 5 that is equal to 3. Let's look at a second example. The reverse way. Let's say we have that the log of 16 in base 4 is equal to 2, and we're to write that in exponential form. How would we go about that? Well, we have to look at this expression and analyze and understand what it means. So the log of 16 in base 4 is equal to 2 is just another way of saying that if you take the base 4, that small little 4 down there, and you raise it to some power, which is 2, it will equal to 16. So that's our answer. 4 to the second power is equal to 16. Now, let's look at some laws of logarithms. You will need to know these, especially for our future lessons. So our first law is that the log of PQ in base A is equal to the log of P in base A plus the log of Q in base A. Again, I know this might look confusing, and what does it mean? Where does it come from? Well, let's look at the exponents equivalent of this first law. You know that if you had 3 to the second power multiplied by 3 to the fifth power, that would be equal to 3 to the second power plus fifth power, which will give you 3 to the 7th. This is this equivalent in logarithms. In exponents, when you're multiplying and they have the same base, then all you do is you add the powers. So equivalently, when it comes to logarithms, you add the two logarithms. So let's look at an example. Let's say you are to find the log of 32 in base 2. Well, if you don't know what the log of 32 is, you can break down 32 into a product of two numbers. So I know that 8 times 4 gives me 32. So I can say that it's going to be the log of 8 in base 2 plus the log of 4 in base 2. Now, 2 to what power gives me 8? Well, that's 2 times 2 times 2. So the log of 8 in base 2 is 3. And what's the log of 4? Well, 2 times 2 gives me 4. So the log of 4 in base 2 is 2. So 3 plus 2, which is the log of 8 plus the log of 4 in base 2, is equal to 5. And that is then equivalent to the log of 32 in base 5. Let's look at our second law of logarithm. The log of P divided by Q in base A is equal to the log of P in base A minus the log of Q in base A. Let's look at the exponents equivalent to that. So you know that if you had 3 to the 8th power divided by 3 to the 5th power, that would be 3 to the 8 minus 5 power, which is 3 to the 3rd power. If you are dividing, then you subtract the indices. So it is the same idea when it comes to logarithms. You subtract the logarithms when you're dividing. Let's look at an example. Let's say you're to find the log of 16 in base 2. Well, we can say that 16 is equal to 64 divided by 4. So that would be equal to the log of 64 in base 2 minus the log of 4 in base 2. So the log of 64 is 6, and the log of 4 is 2. So 6 take away 2 gives us 4. Therefore, the log of 16 in base 2 is 4. Next, our third law of logarithm, the one that has to do with powers. So the log of p to the b power in base a is equal to b times the log of p in base a. Again, let's look at our exponents equivalent. So you know that if you had 3 to the second power being raised to the third power, then you would multiply those two powers. So you would get 3 to the 2 times 3 power, and your answer would be 3 to the 6th power. So here it's a similar idea. You would multiply by that power. That's why you have b times the log of p. So let's look at an example. Let's say we were to simplify the log of 625 in base 5. Well, 625 is actually 25 squared, or 25 to the second power. So that can be then simplified as 2 times the log of 25 in base 5. Now, the log of 25 is simply 2, because 5 squared is 25, right? 5 to the second power gives you 25. So the log of 625 is 2 times that amount, which is 4. Let's look at our fourth law of logarithm. The log of a in base a is equal to 1. Whatever could that mean? Well, let's look at our exponents equivalent. You know that 3 to the first power is equal to 3. If you had 10 to the first power, that would be equal to 10. If you had a million to the first power, that would be equal to a million. In fact, any number to the first power is equal to the number itself. So if you were to find the log of that number in that base, it would just be equal to 1. Because the log of a in base a is just saying what power must you raise a to in order to get a. And since any number raised to the 1 power is the number itself, then the answer has to be 1. So just to look at an example, what's the log of 5 in base 5? That's equal to 1. Our fifth and final law, the log of 1 in base a is equal to 0. Why is that the case? Again, let's look at our exponents equivalent. 3 to the 0 power is equal to 1. 5 to the 0 power is equal to 1. A million to the 0 power is equal to 1. Any number raised to the 0 power is equal to 1, except 0 to the 0 power. But that's for another time. So any of these numbers except 0 raised to the 0 power is equal to 1. Alright? So the log of 1 in any base a will be equal to 0. So the log of 1 in base 5 is equal to 0. The log of 1 in base a million is equal to 0, and so on and so forth. Let's look at a few notable exceptions, right? A few caveats. The first thing to note is that the log of a proper fraction is a negative number. Why is that so? Well, let's take a look at this example. Let's say you have to find the log of 1/8 in base 2. Since it is a fraction, then the log of 1 divided by 8 could be broken up and expressed as the log of 1 minus the log of 8. As we just saw from our fifth law, the log of 1 is 0, and the log of 8 in base 2 is 3. So 0 take away 3 gives us negative 3. If it's a proper fraction, then that means the numerator, the number in the top, is less than the number in the denominator. If it is less than the number in the denominator always, then that number is going to be smaller than the number in the denominator, and consequently the logarithms is going to be smaller. So if you have a smaller number subtracting a bigger number, you will always get a negative. Hence, the log of a proper fraction is a negative number. Another thing to note is that the log of 0 does not exist, as well as the log of a negative number. Why is that the case? Well, let's take a look at a graph of an exponential function. What do you notice about this exponential function here? The graph, it only gets bigger and bigger as you go further to the right. What happens as you go further to the left? It gets smaller and smaller. However, it never actually becomes 0. We say that the x-axis is an asymptote to this graph. It approaches it, but never actually reaches it. And if that is the case, then the logarithm of 0 does not exist, because no number raised to any power will give you 0. Also, if it never actually reaches the x-axis and becomes 0, then it can also never cross it and become negative. So, all the same, the log of a negative number does not exist, because no number raised to any power will give you a negative. The most it can be is a big number, or the least it can be is a very tiny fraction. So with that, we come to the end of our lesson.